In this tutorial, we will focus on signal representations and the difference between signal modes supported in VPIphotonics Design Suite. Specifically, we'll explore block mode and sample mode signal representations. Before diving into simulation techniques, let's revisit two fundamental properties related to signal processing in our simulations. As described in the Optical Systems User Manual, Chapter 4, Fundamental Signal Modes and Representations, our optical signals are described using baseband transformation. It uses the fact that modulation frequency is much smaller than the optical carrier frequency, so that the latter can be separated from the signal and treated as a constant parameter. The remaining part consists of the time-dependent complex amplitude envelope of the optical field. It carries the modulation information for optical communications. The other aspect is that the signals are discretized. To better understand these concepts, we recommend reviewing the signal sampling example under Optical Systems Demos, Simulation Techniques, General, Signal Sampling. Discretized signals are represented using a finite number of samples within a time window, which defines the total duration of the signal. By applying the fast Fourier transform to the time domain signal, we can convert it into the optical spectrum, where the frequency resolution is determined by the inverse of the time window. Another important parameter is the temporal resolution in the time domain, or the sampling rate. It also determines the frequency bandwidth in the optical spectrum. Therefore, the signals can be represented as vectors of complex-valued samples, where each element corresponds to a specific point in time or frequency, depending on the simulation domain, and some additional information like optical carrier frequency, boundary conditions, the time and frequency grid spacing, and others. Block mode and sample mode define how the signal data is exchanged between different components on the schematic. In block mode, data is processed in whole blocks, vectors representing the discretized signals in the time or frequency domains. Each module in the simulation receives the entire time window of samples from the previous module before it begins processing. This sequential processing approach is efficient for long signals and is commonly used in unidirectional optical transmission systems. To visualize block mode operation, first, let's use this abstract system schematic of a single-channel system. Next, we can enable the animation option in the Submit Simulation Job dialog. With this setting, each module on the schematic will be highlighted as it runs, and we can monitor the progress of the simulation. Please also notice that we specified 3 runs. While the simulation is running, we can observe how the signal flows from transmitter to fiber, from fiber to receiver, and from receiver to analyzer. Since we set 3 runs, this signal data flow repeats 3 times as well. This simulation operates in block mode. Block mode is the efficient form of simulation, as modules are only fired when data passes through them. It is best suited for scenarios without tight feedback or dynamic interactions between modules, such as in optical transmission system simulations, where components are widely spaced relative to the modeled time, or where signals flow unidirectionally, as in the case of a transmitter to receiver setup. Other common applications for block mode are modeling passive photonic integrated circuits and FFT-based digital signal processing. Block mode, however, may not capture fast dynamics or bidirectional components interaction effectively. In such cases, sample mode can provide a better solution. In contrast to block mode, sample mode processes data one time step at a time. All modules in the schematic run synchronously at each time step, exchanging one sample at a time. This process is repeated for each sample across the entire simulation, including all iterations and runs. Here we see a typical abstract schematic, where sample mode simulation is important. A laser connected to a waveguide with a reflector at the end, such as from a chip connector or a fiber. This back reflection inevitably alters the laser's dynamics and performance. We can observe the transient dynamics in the simulation results. In general, passing data between modules in sample mode on a sample-by-sample basis is necessary when the delay between the modules is much shorter than a block length. The modules must communicate rapidly in order to fully simulate their joint behavior. At the same time, sample mode may be slower compared to block mode, as the corresponding simulation models often require smaller time steps for accurate results and generally demand more computational resources due to repeated execution and data exchange between modules at every time step. Sample mode is especially useful when modeling lasers with transient dynamics, as in this example, photonic circuits with strong bidirectional coupling and feedback-sensitive systems. The form of signal representation is determined at the optical and electrical signal sources. If a module supports both block mode and sample mode signals, it includes an output data type parameter that allows switching between the two modes, as seen in the DC source parameters here. While most modules operate in block mode, some, such as laser TLM and photonics TLM or the waveguide module, work exclusively in sample mode. Information about supported signal representation is specified in Module Reference Manual Signal Representation section. Both signal modes are widely used in VPI Design Suite. For block mode simulation, you may check the demo A Simple WDM System found under Optical Systems Demos, Simulation Techniques, Getting Started. For sample mode simulation, please check Laser with Feedback Schematic, found under Application Examples, Photonic Circuits, Lasers, and SOAs. It closely repeats the abstract schematic shown before.